We have some new identities today. These are called the sum and difference identities. So we'll be adding and subtracting angle measurements. And I just have them listed out here. And the big thing that I guess I want you to recognize that if I take the sine of two angles that might be added, they might be subtracted, but sine is not something you can distribute. It's not really just the sine of a 30 plus the sine of a 40 or anything like that. You can't add or you can't distribute sine or cosine or tangent. There's actually an identity. If I'm going to take two angle measurements, and usually I'm going to try to make these angles end up landing on my unit circle. So we'll be doing a lot of unit circle stuff today. If I'm trying to find the sine of two angles that are added, then what I have to do is I have to take the sine of the first angle, multiply it times the sine of the second angle. And then this is a plus or minus. It matches this plus or minus. If I'm going to add these two angles together, then I'm going to add here. If I'm going to subtract my two angles, then I'm going to subtract. It's just the same as whatever's going on inside the parentheses. And then notice the second part of the identity, I take the cosine of the first angle and then the sine of the second angle, and I multiply those together. The other cosine is very similar, except it has some key differences. Notice instead of going sine, cosine, on the cosine identity, it's going to go cosine, cosine, sine, sine. So the order of those things is going to be different. The other major difference is this right here. This is not a plus or minus, it's a minus plus, which means you're going to do the opposite of whatever you see in the parentheses. Tangent is different, and it will typically be a little bit different. It's derived from the sine and cosine, which is going to make it be a fraction a lot of the time. And for it, you're going to take tangent of your first angle with the same sine, and then tangent of your second angle. In the denominator, you'll do 1 opposite sine, and then you're multiplying your tangent x and tangent y. Notice those are the same values from up there. Let's look at a couple, just so that you recognize what it's going to be. You have this mess of a thing right here. Now, typically, we're going to have to create this mess. What I want you to recognize in here is what identity would this be? Which one goes cosine, cosine, sine, sine? And if you peek back, I hope you say, oh, well, that's cosine. That's the cosine identity. And in parentheses, you'd have your first angle, which in this case looks like it would be a 5 pi over 12. And recall or look back at your cosine identity that you do the opposite sign here. If that's a minus, then this must have been a plus. And then my second angle looks like it's a pi over 12. And right now, we're just going to practice writing the expression. Now, I could certainly simplify this and keep going, but right now, let's just write the expression. That's what it would look like. Let's try B. Okay, it should be pretty obvious which trig ratio that one is. We should be doing tangent. The first angle looks like it's a 200. And then this sign, remember, matches this sign, whereas this is the opposite. Looks like I'm going to have to put a plus sign. My second angle is a 70. Now, I could go further with that one as well, but I'm not going to. I just want you to see how that sets up. On number 2, I am going to go the next step. I'm going to actually evaluate it when I'm done. Let's look at it. You have to look and decide which trig ratio you see happening. So peeking back, you're finding the one that goes sine, cosine, sine, cosine. All right, that's the sine identity. And in parentheses, my two angles, 15. The sine identity uses the same sign, so it'll be a plus 30. And that's where we stopped earlier, but since I'm evaluating, I'm going to go ahead and add those two angles together, which actually works pretty slick because I know 45, the sine of 45, it's on my unit circle. It's the square root of 2 over 2. We're going to definitely need to know our unit circle stuff. It's going to keep popping up today. Let's go the other direction. Let's say they give us an angle, and we're going to use the identity to evaluate it. And these are going to be angles that aren't on the unit circle. 75 is not one of the angles. But what I'm going to do is I'm going to write that 75 as a sum or a difference of two angles that are on the unit circle. Can you think of two angles that maybe would add up to 75 but are definitely on my unit circle? I hope you say 30 and 45. That's probably the one that jumps out. Now there would be other ways, certainly many other ways to come up with that 75. You could do like a 135 minus a 60 or something like that. But keep your life easy. Use as small numbers as you can. Remember, we cannot distribute. That's not what we're doing here. We are setting up our identity. I didn't leave myself enough space on this. I'm just going to keep going. Equals. Now, the identity says you go cosine of 30, cosine of 45. Keep the same sign. Oh, wait. Nope. Cosine is the opposite sign, so it's going to be a minus sine of 30, sine of 45. And that big old long mess is what we're going to simplify. These are all unit circle things. The cosine of 30 is root 3 over 2. I was making you think. What's the cosine of 45? Root 2 over 2. Minus, now let's do the sine values there. The sine at 30. Oh, where did that 40 come from? That's a 45. And the sine of 45 is root 2 over 2. We go ahead and we multiply those together. That's going to be a root 6 over 4 minus root 2 over 4. Oh gosh, that has a common denominator. I'm going to go ahead and simplify that to a root 6 minus root 2 all over 4. Final answer. We're getting the exact value of the cosine of 75. I obviously didn't give myself enough space, so I just wiped it clean. I'm starting over. Let's do part B. I'm going to start way over here on the left. The sine of 285. I have to come up with two angles that would add up to 285, or we could maybe subtract to 285. What do you think? How about a 135 plus a 150? That would add up to 285. I'm doing the sine this time. Use your sine identity. So if you peek back, it goes sine of the first angle, cosine of the second, and the sine identity uses the same sign, so it'll still be a plus. And then I switch it and I do sine of the second angle times cosine of the first angle. And then we go to our unit circle and evaluate all of that. The sine of 135 is positive, root 2 over 2. Cosine of 150 is a negative, root 3 over 2, plus sine at 150 is 1/2, and the cosine at 135 is root 2 over 2. And then you just clean it up. That's a negative root 6 plus, I'm just going to merge these at the same time because I can already tell I have that common denominator of a 4. You're going to run across, in the same way in the unit circle that we have root 3 over 2 and 1/2 all over the place, we're going to run across the same numbers because we keep dealing with root 3 over 2s and root 2 over 2s and 1/2. We're going to see this looks very similar, with the only thing changing is the sign. All right, let's try one more. Let's do tangent. Tangent is a little messier of an identity because it's a big fraction, but that's okay. I got to come up with a negative pi over 12. Sometimes the radians are hard because they're in fraction form like that. I got to find something that builds up to a 12. And really what I'm probably going to do is I'm going to subtract on this one, but I'm going to take a small number, subtract a big number, and somehow end up with a 1/12. Now I'm going to play with some numbers and show you kind of how you come up with that. I would change all my pi over 3's and think of them as pi over 12. For instance, a pi over 3 is really the equivalent of a 4 pi over 12. So I could somehow use up a 4 pi over 12 to get to that. I could do a 2 pi over 3 and call that 8 pi over 12. You can also work with the sixth. For instance, a pi over 6 would be the same as a 2 pi over 12. Or if I had, let's say, I guess my next one is really a 5 pi over 6, would be the same as a 10 pi over 12. And remember, I'm trying to get something that could subtract to this pi over 12. I don't think I have it yet, but I'm trying to show you what to do with these. Let's try it with a half. What if you had a pi over 2? That would be the same as 6 pi over 12. Or if you wanted to work with a pi over 4, that would be the same as 3 pi over 12. And you're playing with all of these, and you'll get kind of familiar with some of them. I'm going to actually, remember, I'm trying to get this negative pi over 12, so I'm going to grab this one right here and this one right here. I'm going to take 3/12 minus 4/12, and I'm going to get my negative 1/12. Ultimately, what I'm doing then is I'm going to use the pi over 3 and the pi over 4. But I'm going to take the pi over 4 minus the pi over 3. I'm going to write it like this. The tangent of pi over 4 minus pi over 3. And then I'm going to use my identity. I'm going to take the tangent of the first angle. And in the numerator, I use the same sign. It's going to be minus tangent of pi over 3 over. In the denominator, I'm going to have a 1, and then I use the opposite sign, which means I'll want a plus, and then tangent of pi over 4 times tangent pi over 3. And then we fill in the numbers from the unit circle. The tangent of pi over 4 is 1, minus the tangent of pi over 3 is root 3. In the denominator, I have a 1 plus 1 times root 3, which is really just a root 3. And this doesn't come out too bad. Now let me tell you though, I picked some good ones, because if you'll recall from your unit circle, any time that you use the pi over 6, tangent will be root 3 over 3. And root 3 over 3 is going to be like right here, and then you're going to have fractions inside of fractions, and it's going to get kind of messy. If you can avoid that, it's probably worth your time to come up here and spend some time finding something that's going to work with a third or a fourth or a half, and try to avoid the sixth on these. Now, sometimes you don't have that choice. I'm just trying to encourage you to look for something. Now, I'm not happy with this in the denominator because I don't like to have radicals in the denominator. I'm going to multiply by the conjugate. Remember doing this way back at the very beginning? Multiply by the conjugate. The conjugate always multiplies nicely because I'm going to FOIL that. In the top, when I FOIL, I'm going to have 1. The outer is going to be negative root 3, and the inner is negative root 3. That ends up being minus 2 root 3. And last, a negative root 3 times a negative root 3 is a positive 3. In the denominator, multiplying conjugates, I have my 1 for my first, but the outer and the inner, negative root 3 and positive root 3, are always going to drop. Last is going to be a minus root 3 times root 3 would be a 3. Simplify it up, I'm going to end up with a 4 minus 2 root 3 all over negative 2. And just when you thought you were done, we're going to go a little bit farther, and we're going to go ahead and divide here. You can't just like cross these out. This whole thing is being divided by negative 2. That means that you have to take the 4 and divide it by negative 2, and you have to take this term and divide it by negative 2. If I divide them both by negative 2, I would end up with a negative 2 plus root 3. It was messy getting there, but the final answer sure turned out nice. All right, I think in the future I'll have to split this over several slides. I'm sorry that I did not leave you near enough room for that. Let's practice a little bit of verifying. Verifying with the sum and difference identities is usually pretty slick. It falls out just beautifully. Again, one thing you cannot do, the number one rule here, is do not distribute. Immediately go to your identity. The cosine identity, I'm going to start way over here on the left. Cosine of the first angle, cosine of the second. And then I use the opposite sign. Since that one's a minus, this is going to be a plus. And then I do sine of the first angle, sine of the second angle. That's just the identity. That is supposed to end up equaling sine x. Now this is a unit circle thing. This is something I'm just going to have to leave there. Unit circle, I'm just going to have to leave there. Let's go ahead and do that unit circle stuff. The cosine at pi over 2 is 0 multiplied by cosine x, plus the sine at pi over 2 is a positive 1 times sine x. It's supposed to equal sine x, which it will, because 0 times cosine x is going to cancel out, and 1 times sine x is just sine x. We've got it. Sine x equals sine x. Again, boxing that in, but the real answer is in the work. Let's do some simplifying. Just practice using those identities. Not going to distribute. I'm going to jump kind of far on the left here and try to write small. Using the identity, cosine is cosine first angle, cosine second angle. Use the opposite sign, and then I do sine of each. Cosine theta stays cosine theta, and I evaluate the cosine of 3 pi over 2. That's my x value. I'm straight down. That's going to be in 0. Plus sine theta, and then I evaluate from the unit circle. The sine at 3 pi over 2 is negative 1. This is going to cancel, and my final answer would be a negative sine theta. Well, that wasn't as bad. Okay, let's try this tangent one. Tangent is a fraction, so it might take up a little bit more space. I'm going to start right off and do the identity. The identity says that you take tangent of the first one, keep the same sign, tangent of the second one, over 1, and then you do the opposite sign, and you multiply those two tangents together. Now let's simplify that. In my numerator, I'm just going to have that tangent of theta plus 3 pi. Remember, just goes and wraps around and lands the same place as pi. And the tangent there would be 0 over, in the denominator, I'm going to have a 1 minus tangent of theta times 0. Now if you think about this, this is going to work out pretty darn nicely because tangent times theta is 0. So that's just 1 minus 0 down there. And here I don't really need to add that 0. I end up with a tangent theta over 1. That's just tangent theta. That all simplifies out nicely. Okay, this is the fun one here. Take some nice notes. I'm only doing one of these. And they're a pretty common type of use of the sine, or the sum and difference identity. But when you look at this and I tell you that that sine x equals 3/5, the first thing you should be thinking is, well, gosh, 3/5 is not a number off my unit circle, nor is 24/25. And hopefully you think, oh, that's when I have to draw the triangles. Okay, so let's draw some triangles. Sine x equals 3/5. X is in quadrant 1. Let's draw this. X is like your theta, or your angle. So if I'm in quadrant 1, I'm just going to draw in some sort of a triangle, and I'm going to call this angle x. The sine is opposite over hypotenuse. And then you should be able to find the missing side, the adjacent side. That would be 25 minus 9, which is 16. So this side is 4. Maybe you knew that was a Pythagorean triple. Let's try it again. This time, we're going to figure out y. It tells us here that sine of y is 24 over 25. And this time the angle is going to be in quadrant 2. I'm going to put y down here. That's your angle. Sine is opposite over hypotenuse. And you can type that in your calculator or write it out, but you're kind of doing that same deal. You're going to do 25 squared. You're going to subtract 24 squared. And lo and behold, you end up with a 49, which means this leg must be a 7. It's another Pythagorean triple. Not as common as your 3, 4, 5 triangle, but this works out really nice when you have Pythagorean triples because you don't have to deal with the radicals. Now our goal here is to find the sine of x plus y. Whoops, what am I doing there? And we're going to use our identity to do that. Let's start off and say, all right, that's the sine of x times the cosine of y. Keep the same sign, and then you swap them. Sine of y, cosine of x. That's the identity. Let's start filling in some numbers. The sine of x, well, I go up here to x, and I say, well, the sine is opposite over hypotenuse. In fact, that was one of the ones they gave me, 3/5. And I just replace that then with a 3/5 times, let's do it again, cosine of y. So here's my y. Cosine is adjacent over hypotenuse. Plus, back to the, or I guess I'm back on sine. Sine would be opposite over hypotenuse. 24 over 25. And then I'm back over to x. Cosine is adjacent over hypotenuse. Now we're going to multiply. And sometimes you might look to reduce these, but I would recommend that you not, because we're eventually going to have to add fractions together, and you'll want a common denominator. A lot of times if you try to reduce here, you end up having to build it back up when you get your common denominator. Wait to reduce and later. I'm going to multiply this. That's going to be 21 over 125 plus 96 over 125, which can then combine (117) over 125. Okay, that, just to clarify, what did we just find? We found if we were to add this angle to this angle, and then go find the sine value of it, it would end up equaling this value right here. What I've managed to do is go ahead and get that as an exact value versus if I were to go type something in the calculator and get decimals for it. Which is really what we're doing in this whole thing with using this sum and difference identity, is we're finding exact values with radicals or whatever rather than getting decimal approximations. All right, that's all I've got for you. Go have fun, do your homework.